Now this next section, 6.2.2, is kind of fun. It has various inequalities for estimating probabilities. And rather than following his discussion, which is pretty opaque, although it's quite clear, I want to give you some proofs that I came up with. And I call these piles on a seesaw. Now they're not exactly proofs, but the arguments can be refined to give proofs. And I think it gives some insight into what's going on. So I kind of like to show these this way. All right. So first of all, I'm going to prove the Markov inequality, but let's put that aside for a moment. Just consider this scenario, and let me move this out of the way because I won't be using that. Suppose I have a pile of probability sand with total weight 1. So just think of a pile of sand, and I have to distribute the sand on a massless seesaw whose left-hand endpoint is at 0. Okay, so let's start to draw my picture here. Let's do here, I've got my seesaw, and the left-hand endpoint is at 0. Okay. All right, so I'm going to make a seesaw. Just to tell you, I'm going to want to balance this seesaw. But I have to place the weight on, and I have to distribute the weight evenly. Now, the total weight that I'm distributing is 1. And I have to distribute the sand on the massless seesaw whose left-hand endpoint is 0. I'm only allowed to place a weight of up to 1 minus p on the interval 0 to a. All right. So if I go up to a here, I can only put a mass 1 minus p over here, and I have to put a mass p over here somewhere. Mass p to the right of a. And I have to have mass 1 minus p, or mass less than or equal to 1 minus p, to the left of a. Now, so I have to have at least p to the right, and I have to have 1 minus p to the left of a. All right? So I'm going to put some mass over here to the left of a, some mass over here to the right of a. It can be over here at 0. It can be anywhere on this interval here. Okay? 1 minus p can be anywhere on this interval from 0 to a. But p has to be to the right of a. Okay. Now I want to put a balance point, right? So you have a seesaw has a balance point. So just imagine this. So I want to put the balance point somewhere in here, and I want to put the balance point as far to the left as possible. So you can try this, get a ruler, get some stuff to put on it, and where you're going to put the balance, or you just take your finger and a ruler, and think about putting weights on the ruler, and think about this problem. And you're going to put weights on top of the ruler, but you want to have the balance point as far to the left as possible. Right? So how am I going to distribute the weights in order to make the balance point as far to the left as possible? So if you think about that for a minute, you can pause the video. But the answer is, I want to put the weights as far to the left as possible. So to put the balance point as far to the left as possible, put the weights as far to the left as possible. Now, what does that mean? Well, let me redraw my picture again. Let me move this down. Okay, so here we go. Redraw my picture. I have 0 here. I have a here. Now, in order to put the weights as far to the left as possible, I have to put a weight 1 minus p. I can put the weight 1 minus p over here on 0, and I can put the weight p on a, right? So that's going to make the weights as far to the left as possible. Now, where is the balance point? Well, the balance point is where you have your weight and your lever arm, right? So if I have I have to put this in order so that these two balance. Okay. So let me call this distance here, I'll call this distance x, and this distance here will be a minus x. Okay. And I'll have to solve for x. Where it balances, I'm going to have the lever arm to the left is equal to the lever arm to the right. What's the lever arm to the left? I would need 1 minus p times x is equal to a minus x times p. Okay. And of course I can use that, I can solve for x here. Okay. And let's see, I have to rearrange here. So I'm going to have 1 minus p times x on the left-hand side, and then it is equal to ap minus ax. I'm sorry, ap minus px. And in fact, if you think about it, the px here cancels the px here. So I'm going to get x is equal to ap. I got to get rid of this pesky stuff again. Okay, now what does this have to do with probability? Well, this balance point is the mean of the distribution of the weight, right? That's where you can balance a seesaw. So x is equal to the mean of the probability distribution. Okay, and I can consider this probability distribution as the probability distribution of a random variable x. Okay, all right, so that means that x here is going to be equal to the expected value of x. Okay, so what do I have? I have expected value of x is equal to ap for the distribution above. Okay, now I said this is the distribution that has the expected value, has this point to the leftmost possible. So this is the leftmost and that's leftmost in this case means smallest because it's closest to 0. The leftmost value for e of x. Okay. So what does that mean? That means that in general, e of x is going to be less than or equal to, greater than or equal to, because that's the leftmost. Okay, it's going to be greater than or equal to AP. Okay, now I can rearrange this, and this tells me that P is less than or equal to E of x over A. Okay? Now, in fact, this is the Markov inequality. So what is the general situation we're looking at? Okay. I'm talking about the expected value of a random variable. So my random variable, what about my random variable? Well, I said that the mass has to be distributed on the seesaw. So x is a random variable. And the seesaw has left endpoint at 0. So it's a random variable that takes values on the positive interval, 0 to infinity. Okay. So that's really the only condition I have on x. And that P means the probability that x is greater than or equal to A. Okay? All right. So I wrote this P here. So in general, the probability that x is bigger than or equal to A is less than or equal to the expected value of x divided by A. Okay? So just think about this seesaw argument. The reason why we can bound the probability that x is large is because that's the best way to make the expected value small is to move all the probability that you can to the left. Okay. So if I know that the probability here is P, so you can say the argument's a little bit, it goes around kind of around the back door, but it does tell you the relationship between the expected value and the probability. When I derived the expression, I found a bound on the expected value, but I can rearrange that to give me a bound on the probability. Okay, so you can read that statement also in the chapter. The chapter says the same thing, right? Okay, so that was pretty cool. What we did was, using this scenario, we found a bound on expected value, and we turned that around to give a bound on probability. All right, so eventually we came up with this result here. Now, how about we do the same thing with variance? And we'll do another scenario and use the variance in order to get another bound. So let me size this a little better. Okay. So this is the Chebyshev inequality. Move it over. Here we go. Just got it there. All right, so let me shrink it a little bit. Sorry, I thought I had this sized well, but I guess I didn't. Okay. Let's just move it over and we'll shrink it this way. Just give me a moment and we'll make this a little bigger. Okay, there we go. So that should do it. All right, now suppose I have a pile of probability sand with total weight 1, same as before. And this time I have to distribute the sand on a massless seesaw, same as before. So the balance point is at 0. Okay, so now I'm balancing in the middle at 0. And the seesaw goes to the left and to the right. So I'm only allowed to place a weight of up to 1 minus p in the interval minus a to a. I want to distribute the sand so the mass is distributed as close as possible to the balance point as possible. So the question is, how do I distribute the sand and what is the variance? All right, so what's the scenario here? I've got my seesaw here and it's massless, so don't worry about the length of the seesaw. And I have my balance point at 0. And I have my interval from minus a to a. And I can put a probability mass of 1 minus p in here. But I have to put a probability mass of p outside of this interval. So where do I put this probability mass of p? So the best way to put the probability mass is put it in as close as possible to 0. So I want to put the mass of probability p as close to 0 as possible. Okay. Now how can I do that? Well, one way to do that would be pull it into A. Now I'm going to have to balance it, so I could put p over 2 over here. I could p over 2 over here, and I could put the 1 minus p in the middle. All right? So I guess I have to change my color here. This is at A. This is at minus A. So the probability mass here, I guess I'll switch back to green. Okay, the probability mass here would be 1 minus p. The probability mass here would be p over 2. And the probability mass here would be p over 2. Okay. So that's how I can distribute my mass to be as close as possible to the center of the seesaw. Okay, so what is the variance? Okay, now you can see that the way I arranged this is that the weights are arranged so that the mean of this distribution is 0 because it's symmetric. So the distribution is symmetric. So the mean is equal to 0. Okay. Now what's the variance? Well, the variance, if you remember, it's going to be equal to the sum over all possible values of the value. So I'll call these values, I suppose I'll call them xi. It's going to be xi minus e of x. Okay. And then that's times p of xi. Again, I'm taking this distribution as representing the distribution of a random variable. Now in this case, e of x is equal to 0 because that's the mean. Okay. Now I have to sum up the probability. So I actually have three values. So in this case, it's going to be, this should be a square. It's going to be equal to minus a squared, right? Because I have this value minus a minus 0, so that's minus a squared, and that's going to be times p over 2. Okay. Then I have the value 0, so that's going to be 0, and that's 1 minus p. That's, well, 0 squared if you want to say that. And then the value on the left is a squared times p over 2. All right? So you can see minus a squared and a squared just gives me a squared, so I'm going to get 2 times a squared times p over 2. So it's equal to a squared p. Okay. So I can write the variance of my random variable, because this is a probability distribution of a random variable. The variance of x in this case is equal to a squared times the probability, a squared times p. Now remember, p is equal to, is the probability that x is greater than or equal to a. But it's not just x, it's absolute value of x is greater than or equal to a. Okay? All right, now remember, what I've done here is I've arranged the mass to be as close to 0 as possible. Okay? So this is the smallest possible variance. This is the smallest possible variance for a random variable which has probability mass p of x greater than or equal to a. Or probability mass p outside of minus AA. Okay? All right, so in general, the variance will be greater, right? If I change the distribution of x, the variance will be increased, okay? So in general, okay? So that means that the variance of x is greater than or equal to a squared times the probability that x is greater than or equal to a. And now I'll turn this around again to get a bound on my probability. Okay, just divide by a squared, so the probability that x is greater than or equal to a is going to be less than or equal to the variance of x divided by a squared. Okay, and this is the Chebyshev inequality. All right, we're on a roll here. We have two scenarios that gave us two inequalities. Let's see if we can try for three. All right. Now, in this scenario, I said that the sand has to be outside of the interval from minus a to a. And I used variance to get an inequality. Now, in the first scenario, I said that the mass has to be to the right of a, and it had to be a positive random variable. So that gave me a bound. Now I'm going to kind of combine these two. I'm going to limit the probability that the mass is to the left of A, and I'm also going to allow the mass to be on the negative side. So here's my third scenario. Okay. All right, so suppose I have a pile of probability sand with total weight 1. I have to distribute the sand on a massless seesaw, so the balance point is at 0. I'm only allowed to place a weight of up to 1 minus p to the left of A. Okay, so I have no restriction of being in the interval minus a to a, but I have to place only 1 minus p to the left of A. And I want to distribute the sand so the mass is distributed as close to the ballast point as possible. How do I distribute the sand and what's the variance? Okay, so let's draw my picture again. Let's see what color we are now. So here's my balance point at 0. And I have a mass, I have here, and I have to have a mass P to the right of A. Okay. All right, now I want to move this as far to the left as possible. All right. Now, I don't think I even need to redraw the picture. I'm certainly going to want to put all that mass here, right here. So I'm going to have a probability mass P right here. Okay. Now, the expected value is here at 0. So I'm going to have to put some mass to the left in order to balance this and make the mass be equal to 0. Okay. So I'm going to have to put some mass over here, and I want to move it as close to 0 as possible. So I'm going to have some mass 1 minus P over here. And I don't know how far this is. So I'll make this my unknown. I'll just use the letter X again. Okay. So I have 1 minus P at X, and I have P at A, and I want the expected value of this random variable to be 0. So the expected value of the random variable that has this distribution should be equal to 0. So that tells me, and you have this general formula, the sum over the possible values, xi of xi times p of x equals xi. Now, what are the possible values for your random variable? Well, I'm going to have, let me call this minus x here because it is going to be negative. So the values are minus x and a. Those are the two values of my random variable. Okay. So I'm going to have minus x times 1 minus p. And then I'm going to have plus a times p. Okay. So that's my expected value. So that has to be equal to 0. So let's solve for x. Okay, so what value do I get for x? Well, I'm going to get x, I'm going to get minus x is equal to minus ap over 1 minus p. So that means that x is equal to ap over 1 minus p, just by some algebra. Okay. Now, what's the variance of my random variable? Okay. How do I compute that? So that's equal to the sum over values, xi, of the value xi minus expected value of x squared times the probability that the random variable x equals xi. Okay, so I plug in my values. My two possible values xi are going to be minus x and a. So the first one is going to be, I can put a minus x here, and then my expected value is 0. And the probability that x is equal to minus x is equal to 1 minus p. And then my second value is a, right? The rest of my probability mass is up here. So my second value is a squared, and then this has probability p. Okay. Now I also have what x is. X is ap over 1 minus p. Okay. So that's equal to ap over 1 minus p squared times 1 minus p plus a squared times p. All right, let's do some rearranging here. I certainly have 1 minus p canceling, so that's equal to, and I have a squared, p squared, and one of the 1 minus p cancels, so I have a 1 minus p here. And then I have plus a squared p. All right, now I can certainly factor out a squared p, and then I have left here p over 1 minus p, and then have plus 1, and I'll write the 1 as 1 minus p over 1 minus p, so I can combine the fractions. So I have p over 1 minus p plus 1 minus p over 1 minus p. So that gives me a squared p over, let's see, 1 minus p. Okay. So my final result is that the variance of x is equal to a squared p over 1 minus p. And that's the same thing as the variance of x is equal to a squared times the probability that x was greater than or equal to a squared, a divided by 1 minus the probability that x is bigger than or equal to a. All right. Now, this was the smallest possible variance. Now, in general, the variance of x will be bigger. Okay. Okay, so how does that work? Well, that means that the variance of x is greater than or equal to a squared times probability of x greater than or equal to a over 1 minus the probability x greater than or equal to a. All right, so you can simply rearrange this algebraically and get an inequality for the probability that x is greater than or equal to a. Okay, and I won't do that. That's an exercise for the reader or the listener, but you can see that we can get this inequality just by doing this. Now notice that the denominator here is positive, so you can multiply both sides by the denominator and preserve the inequality. Okay, so that's it for these 3 inequalities. Very nice set of inequalities.